Test, 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 bum, 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 bum. Testing. Testing, testing, testing. Maybe it's... Yeah, so I've got it now. I plug in my good microphone. And is it... Alright. Fortunately, I have two backup microphones. I'm hoping it's just the cable. That would be the most... The best case scenario is that's just the cable that's gone on this bloody thing. Well, no good sound quality today, I'm afraid, unfortunately. Yep. Sorry about that, guys. Well, it's, like, I've got the condenser mic, right, which is obviously the good quality microphone. But the webcam that I bought also has one embedded, which is the one that I've currently set it to. And I've also got one embedded in the laptop itself, of course. So I've got I've got two backup microphones and one backup camera, just in case things go completely pear-shaped on us. Yeah. There we go. Well, that's irritating. I hope I don't have to order a new one of those things. I mean, it wasn't that expensive, and maybe that's the problem. I just have to replace the microphone, not the articulated stand, but still a pain. Boy, let's see if there are any announcements today. Good Lord. Nope, no announcements. Oh, heck yeah, this is... Okay, so 4. I've got 4 redundant microphones then. Yeah. Actually, this one might be better quality. Let me see. Do I have access to it? You guys let me know. It doesn't show up. I think I might need like a special splitter. I think my audio jack isn't a combo, so oh well. Sometimes my audio interface won't pick up a signal from my PC, so my condenser doesn't work sometimes too. You know, maybe I just have to like turn it off and on again. That's sometimes the case. But anyway, as long as we can have a microphone working, I suppose that'll have to do for today, and I'll try to get the better sound quality back for next week for you guys, eh? Incidentally, let me know if the stream jumps into a lower quality setting, because right now I've got it set to not ultra low latency, but low latency mode. So that cuts the latency on these videos from 30 seconds to about 10 seconds, which is much more reasonable. The latency was like the one reason that MS Teams had any degree of advantage whatsoever over Teams had any advantage whatsoever over YouTube. And now that YouTube has low latency, and that seems to be working quite well, I think that there's absolutely no point on which Teams is superior to YouTube. Aside from the fact that you guys can't use your voices to ask me questions. You'll just have to use a keyboard, but that's a sacrifice I'm willing to make. So, so last time around, we were talking about a bubble sort. We were talking about sorting algorithms in general. Yeah. Oh, that's funny. The poll would start before the before I would announce it. That's like by 20 seconds. That's funny. So no latency on polls, but latency on the video feed. Yeah. So, bubble sort then. We already kind of described the algorithm somewhat hastily at the end of class last time, so I'll go through it again. Hopefully we'll get through all of these different algorithms by the end of the hour today, so let's keep it moving, eh? So the idea with bubble sort is you look at each individual pair of elements in an array and make a determination about whether those need to be swapped. Are they in the correct position relative to each other? So this has the effect over time of values sort of bubbling up through the bubble sort algorithm. Actually, Wikipedia has a pretty good animation. If you, whenever you're trying to learn a new sorting algorithm, I recommend looking at Wikipedia because they've got like good animations of how sorts go. So you look at bubble sort. Herbert. Should be an animation on this page somewhere. Yeah, well, that's a slow animation, but that also gives you the idea. Here, this is the one I'm looking for. This is what bubble sort looks like. So you'll see that the bubble sort algorithm, its primary objective is that you have a sorted section of the array starting at the top and moving down consistently throughout the course of the algorithm. Regardless of the positions of the particular things within the sort, or within the array, after each pass of the algorithm, like, nothing past the sorted point you need to worry about. And that's the idea with bubble sort, is that after each pass, one more element is sorted. Of course, this means that bubble sort is not the most efficient of sorting algorithms, but it is one of the easier ones to implement. I like the animations with the big whoop sound at the end when all the columns are sorted. Well, I'm afraid you'd probably have to look at a video rather than just an animated GIF if you were to expect any sounds. But you can see it's the reason it's called bubble sort is because values bubble up in it as the sort is performed. You can see things sort of rise to their final placement. So yeah, so this is a complete bubble sort algorithm that I've done out for you guys, and indicating what swaps need to occur when. It's a GIF. I said GIF. So let's conduct an analysis. The number of swap operations we required in the previous example was 13. This is going to be interesting and important because we're going to compare different sorting algorithms and the number of swaps that they have to perform in order to sort the same array. The total number of examinations was 21 for an array of size 7. So we looked at two numbers 21 times, and of those 21 times, 13 of them resulted in actual swapping operations. For each additional element to in the array, we add n minus 1 to the total number of examinations. So you can imagine if we had one more array, or one more element in this array, we would need one more column sort of on the left side here, right? So every time you add another element, you're adding n minus 1 more examinations and potentially more swaps. This means that the total number of operations is proportional to the square of the size of the array. Even though this is triangular, there are a bunch of them that we don't have to worry about. We say that the total number of examinations, or the total number of operations, is proportional to the square, right? Because it is proportional to the square. If it's, half of n squared, right? If it's n squared over 2, that's still proportional to n squared. It's, you just have this sort of what we would call a constant term hanging off the end that we don't really worry about. We say that the complexity of this algorithm is big O n squared. We're going to talk about big O in the next section. Bubble sort can't tell the number of swaps that are needed before it makes a pass. People sometimes have this erroneous impression of computers that they know anything about anything. Computers do not know what the contents of an array are unless you've written an algorithm that picks out the particular property that you're looking for and then run that algorithm. Then the computer knows, but otherwise it doesn't know what the elements are. Bubble sort can't tell the number of swaps that are needed. The same number of examinations will occur regardless of the orderedness of the array. Therefore, we say that the best case runtime is equal to the worst case runtime. So with bubble sort, it's a very stupid algorithm. One way of saying that is it's a simple algorithm. Another way is that it's not a very intelligent algorithm. As we're going to see, you can actually improve the runtime of these algorithms based on a property that we're going to examine called sortedness. Basically, if the elements in the array are closer to their final position, the algorithm, in the ideal case, will take less time to execute. So, big O notation. The mathematical analysis of the performance characteristics of algorithms is an entire subdiscipline of research within software engineering and computer science. So, in order to understand big O notation, you have to kind of understand what problem it's trying to solve. And it's a measurement problem that big O is trying to solve, right? It turns out that it's actually quite different. It's quite difficult to measure how software performs. There are too many factors at play, basically. Consider the bubble sort algorithm. If I were to execute that bubble sort algorithm on my very nice, very shiny, brand new this summer computer, it would take X amount of time. If I were to run the same algorithm on my old clunker that I was replacing over the summer because I literally wore out the spacebar key, shows you how much programming in Haskell I do, that would take a different amount of time. So the amount of time that it takes for an algorithm to execute is highly dependent on the system you're executing it on. This should come as no surprise. Memory is somewhat more stable, but runtime itself can vary widely between different computer systems. Obviously, the same computer with different operating systems will have different runtimes. If you have a Windows operating system, things don't run as quickly on Windows. That's just a fact of life. Something like a comprehensive survey of all computer systems is impractical. It's because that would be one scientific approach to solving this problem is if you have different runtimes on different computers, then just try all of the different computers. And it's like, well, not exactly a practical solution because there are so many different types of computers and each one is going to have its own characteristics. So, the algorithms community has made some decisions about what is important and what is unimportant with respect to measuring algorithm efficiency. Generally speaking, the time it takes a system to execute an instruction is unimportant, compared to how quickly the runtime grows with respect to the size of the input. That is the key idea here. We're not interested in how long it takes any particular system to execute any particular instruction. What we're interested in is how quickly the amount of time you need grows relative to the size of the thing you're executing it on. So it's sort of like, take the size of the array as a variable, right? If you think about an algorithm as executing over an array of arbitrary size, this class is just Windows and Python slander. That's right, and don't you forget it. So, if you have an array of arbitrary size, right? Say the array is size n. Then you can chart n, right? It'll be a linear function. The runtime, hypothetically, will grow with, it'll be some other function, right? If you were to graph runtimes versus the size of the array, in the case of bubble sort, you would have an exponential, well, it's actually a parabolic. It's a parabolic function, right? You would have the runtime parabolically increasing over time. So obviously that means that it's increasing the rate at which it increases. The rate at which it increases the more elements there are in the array, right? The more it is, the faster it grows. Generally speaking, that's okay, but we can do better. So, what is meant by size of the input? Generally, this refers to the size of the data structure the algorithm is applied to. In the case of just plain arrays, we are talking about, just the size of the array. In the case of bubble sort, the size of the input is the number of elements, the number of items that are in the array that need to be sorted. In general, the relation of the input to the runtime can be expressed by a mathematical expression. Consider the following equation. R is equal to A times n squared plus bn plus c. For the purposes of classifying algorithms, we are concerned, only with the largest term in the expression. So this is another simplification that's being performed when we're talking about big O notation. When we are concerned primarily with what one of these terms in this equation will be the dominant one at large n, right? So as n becomes stupidly large, like number of tweets tweeted in a year type large, these things start to matter, right? And the only term that really matters at that point, at that level, is going to be the biggest one, right? That's going to overwhelmingly dominate the runtime characteristics. So generally speaking, when we type something as a big O notation, we only consider the largest term in the equation, and we don't care about the constant term. So this is because for large values of n, the runtime will be mostly, even overwhelmingly, determined by the term with the highest power of n. We don't care about the constants a, b, and c. This is where the individual differences between computer systems will show up, right? So the constant terms, if you were to take the time to calculate out what the constant term would be for this equation, that's dictated by how fast your processor is, right? The constants are also affected by the specifics of algorithm implementation. So, if you're using 3 assignment statements to perform that swap versus 5 assignment statements to perform that swap, that will show up in the constant term. It doesn't give us a good idea, like, it doesn't tell us much about the overall structure of the algorithm. Reducing these constant terms is an active and important area of research. So it's not like the constants don't matter. They do matter. Like, most of the progress that's been made, like, against the p equals np problem is specifically specifically reducing the constant terms, because unfortunately people have more or less come to the conclusion at this point that we're not going to be able to find a polynomial algorithm that solves non-polynomial problems. But you know, that's kind of getting into areas of algorithms research that are a bit. I need to continue on here and keep going. But yeah, so in terms of bubble sort, the power of n is how many times you have to examine / swap things. The constant term is how long it takes you to examine or swap things. And obviously, like, that constant term is going to depend as well on, like, the particulars of the array itself. It takes longer to perform a swap than just an examination. So if you have an already sorted array, that's not going to take as much time to process as something where the worst case scenario for bubble sort is the array is sorted in exact opposite order, but you don't know it. So you have to, like, swap, like, every operation as a swap operation. You know, if you knew that it was in reverse order, you could just reverse it, but, you know, you don't know that. That's the whole point of sorting. But yeah, so back to big O. An algorithm's runtime is abbreviated into big O notation. That's the correct way to think about big O, as an abbreviation of an algorithm's runtime complexity. We often refer to this as the complexity of the algorithm. The complexity can be different in best, worst, and average cases, and this can matter. So, as we're going to see a bit later on, when we talk about insertion sort has a best case runtime of big O n, so n to the power of 1, which can be a useful property. We can often tell what the complexity is by looking at the structure of the algorithm. So looping algorithms are typically big O of n to the power of k, where k is the number of the degree of nestedness of the loops. See, the thing that makes bubble sort big O n squared is because you need a loop within a loop to be able to do this, right? You need one loop that's performing these, like, passes, and you need another loop inside of that loop which is going through each of the individual elements of the array. So you have two nested loops, so it's anything that's inside of the inner loop is being run n squared times, right? So it's a big O n squared algorithm. It's actually not a, like, I know this might be that wasn't the cat, actually, that was the kid. But yeah, so it's not too bad conceptually, even though you can get lost in the weeds with this stuff. Recursive algorithms, which reduce the size of the input by half every step, are generally big O log base 2n. So logarithmic, like, for something to be less than n, like big O of some power that's less than n, that's your golden zone for algorithms. That's the absolute best case scenario, so to speak, for an algorithmic complexity of some algorithm you're trying to implement. So if you've got, like, big O of x to the like square root of x, that's good. If you have big O log x, that's even better, because if you take a look, if you were to graph these over time, like O factorial, that's, like, good luck, man. Good luck if it's big O n factorial. That becomes problematic very quickly. 2 to the power of n is equally terrible. Generally speaking, these are like non-polynomial time algorithms. That's what NP means, by the way, in algorithm. Like, probably some of you have heard of the P versus NP problem, right? So what that actually means, NP stands for non-polynomial. So the idea is, like, the overall goal of algorithms research is to bring these functions down, right? You want to bring these functions as far down as possible, right? Because the thing about these things is you do eventually hit the limits of physical computation, and the complexity of the algorithm dictates how quickly you will hit the physical limits of computation for a particular algorithm. So these NP-hard problems, which have non-polynomial solutions, these guys are like you can hit the limits of computation very, very quickly. Whereas if you have something that's logarithmic, for example, something that's logarithmic takes less time the more things are in it. Well, the rate of increase as you increase. So, okay, let me back up. With a logarithmic function, the more elements you have in the bigger n is, bigger n's result in decreased increase in the runtime. So you actually get more efficiency out, per unit input as you get more of them, which is an interesting property. So what is the physical limit of computation? It will depend on your computer. I'll tell you very briefly, though. One of the big problems in computer science is something called the state explosion problem. The state explosion problem is what makes encryption and passwords work, but it's also, like, it would be really convenient to be able to solve the problem, because then we would, so many limits would be lifted. Is it when the computer will crash? No, the computer doesn't necessarily crash. Like, let me give you an example. Let me pull up. So I'm going to use Google as a calculator here. So a tweet contains 140 characters. Let's be generous and say that they're using 16-bit encoding on these characters. Let's assume they're using Unicode characters, right? So there are 2,240 bits per tweet, right? So how many possible tweets is that? It's 2 to the power of that, right? 2 to the power of 2,240. Oh, you're gonna do this to me, are you? 2 to the power of, where is it? There we are. 2,240. Infinity. Yeah, it isn't actually, but okay. What if we knock that down to 8 bits, eh? 2 to the power of 1,120. Still infinity, eh? So you can do the multiplication out yourself, but the idea is, if you wanted to check, like if you wanted to run some test against every possible tweet, it would take, like, it would take 1 second for every atom in the universe if each atom in the universe contained another universe, and each atom in those universes contained other universes, and each of those atoms contained other universes, and you had like 1 test case per atom in that universe, like 5 or 6 universes deep. That's like the scale of the numbers that we're talking about here. So like it's often not a case of like the computer will break if you try it. It's often the computer will run forever if you try it, and eventually the thing will decay, in the inevitable collapse of human civilization as the sun expands to absorb the Earth. If you find Google Precise Calculator. Oh, that's cool. Well, we have to continue on with this. So let's talk about insertion sort. I don't think we're going to get to searching algorithms, so we'll probably have to cover that after the break. But let's do insertion sort. Insertion sort is really cool. I like it. Computer will become space heater. Yes! If you took the computer and you launched it into space and you aimed it at nothing, and it was able to escape the expansion of all of the stars and the heat death of the universe and somehow still have a power supply. I'm not sure how many, universe cycles it would take to be able to process all of that information. And of course, for us poor mortal humans, it's not really, it becomes, at a certain point, it becomes irrelevant to us, But that's the kind of largeness of numbers that you can get into with these types of problems. So, insertion sort. Bubble sort works, but it contains redundant examinations. It looks at things and doesn't swap them all the time. Insertion sort minimizes the number of examinations that do not lead to a swapping operation. So the purpose of insertion sort is to minimize the number of times you look at things and not have to swap them. Insertion sort only makes one pass of the array, sorting it as it goes. The overall algorithm is to examine each element in the array, passing the element back through the sorted section of the array until the correct spot is found for it. So, in contrast to bubble sort, which kept a sorted section at the back and added to it over time, in insertion sort, we keep our sorted section at the front, and we put things into the sorted section in their correct position as we find them. So, this is the algorithm a little bit more rigorously defined. For each element of the array, the unsorted element is compared to the largest element in the sorted array, which will always be adjacent to it. If the unsorted element is smaller than the element T, the element it has been compared to, those two elements are swapped, and the unsorted element is then compared to the next largest element in the sorted section. This proceeds until the unsorted element is greater than or equal to the element it has been compared to. This means that it has been sorted, and you can move on to the next unsorted element. At this point, the size of the section of the array we considered sorted increases by 1, and we examine the next unsorted element. I found the value, but it's 675 characters, so it can't go in YouTube chat. Yeah. So so this is what you do. You take that number, right? You assume that you can compute 1 million cases per second, right? Which is reasonable right now. And then you multiply that, then you divide by the age of the universe so far in seconds. And that'll tell you how, you can also divide it out to see how many years that becomes. But yeah, you can do the math. So this is how insertion sort works. Same array, you'll notice that the only, as opposed to bubble sort, which contains something like 7 redundant examinations, insertion sort contains 4 examinations which do not lead to a swap, and none of them are redundant, because when we have a swap, when we have an examination that does not lead to a swap, we know that that's the end of that. We know that that unsorted element has become sorted, so we can move on to the next one. It ends the column, right? So this is how it works. We examine the first 2. They get swapped because they're in the wrong order. We then look at the next element, which is 7. 7 is less than 9, so we swap them. 7 is greater than 4, so we leave it and move on to the 1. 1 gets swapped, swapped, swapped. Since it's swapped to the end, we know we don't need to examine any further. We go on to the next one, 7. 7 is swapped into where the 7 is, and then that chain ends. 3 gets swapped, 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 and then 3 is greater than 1, so we leave it. And 6 gets swapped, 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 and then it's fine. So this is insertion sort. The number of swap operations we require for insertion sort is 13. The total number of examinations was 17 for an array of size 7. So, you'll notice that we have definitely reduced the number of overall examinations, but we have not reduced the number of swaps required, right? In bubble sort, we required 13 swaps, and in insertion sort, we also required 13 swaps. With bubble sort, the operations it takes to sort each element decreases with the size of the sorted section. With insertion sort, the operations it takes to sort each element increases with the size of the sorted section. So, as the algorithm goes, bubble sort requires more time. The more elements, it requires more time at the beginning and less time at the end. And insertion sort requires less time at the beginning and more time at the end. Insertion sort is what we call an adaptive algorithm, since its runtime is dependent on the sortedness of the array. Sortedness is a measure of how far off the array is from a sorted configuration. Sometimes this is referred to as degree of disorder. The number of swaps performed in either bubble sort or insertion sort is a direct measure of sortedness. So each one of these swaps puts at least one element closer to its final configuration. So the number of swaps under bubble sort or insertion sort is the degree of disorder in the array. Basically, if you took each element and summed the difference from its final position, that would also be a measure of the degree of disorder. So, best case, worst case analysis. One candidate for the worst case analysis is an array in descending order. So if we have it in descending order and we want to put it in ascending order and we don't know that it's in descending order, this would be a worst case scenario. For bubble sort, every examination would lead to a swap. Insertion sort would require the same number of swaps, so the worst case runtime for insertion sort is big O n squared, the same as bubble sort. So in the worst case scenario, insertion sort performs as poorly as bubble sort. But let's consider the best case scenario. The least disordered array, or best case scenario, is an array that has already been sorted, that you don't know is already sorted. For bubble sort, no examinations would lead to a swap, but it would still make all of the examinations. Insertion sort only performs one operation per element, checking to see that it's correct. This means that the number of operations performed is proportional to n to the power of 1, where n is the n is the length of the array. The computational complexity, then, in the best case scenario for insertion sort, is big O of n. Whereas, in the best case scenario, bubble sort would still take n squared. So there you go. Insertion sort is therefore a much better sorting algorithm. But let's see if we can do even better. Let's talk about shell sort. Incidentally, it's called shell sort not because you make a software shell and play a shell game. It's because the person who came up with it, their name was Shell. So that's why it's called shell sort. It's named after a person. Although insertion sort is an improvement over bubble sort, the number of swap operations that must be performed has not changed. This is because each swap addresses only one unit of disorder. So whenever we swap, we're only swapping things adjacently. Why would bubble sort still be n to the power of 2 if it doesn't do any operations? Aha! Examination is still an operation. It still requires time to examine, right? It requires more time to swap, right? Put it this way, right? If you examine without swapping, you still have to evaluate equality and perform like jumps. And I'm talking about this at like the assembler level, right? You still have to like jump to the end of the if statement. That's an operation. If you have to perform a swap, you have to examine, you have to perform the equality test, set up a temporary variable, and it's a 3 assignment operation to perform a actual swap. So you've got like 5 operations going on there instead of 2. But 2 is still not nothing, right? So examination takes time as well. So in both insertion sort and bubble sort, we're only swapping elements that are adjacent to each other. So we are only addressing one unit of disorder each time we make a swap. It may be possible to increase our efficiency by performing swaps between array elements that are not adjacent. In shell sort, we extract a subarray, sort it, and then put it back in place. By selecting elements that are positionally distant, we can reduce large amounts of disorder quickly. Shell sort is often used in embedded systems applications. Hey, you mechatronics people! Shell sort is often used in embedded systems applications. Why? The code to implement it is small, it is memory efficient, and it doesn't need the call stack. So, shell sort is actually, like, although it's now considered like one of the older algorithms, and you'd never see something running on a PC using shell sort necessarily, shell sort is still like right up there for like best sorting algorithm for embedded systems applications because of its memory efficiency. So we're sorting things that are not adjacent to each other. We're sorting things that have some positional distance. So we need to establish this concept of positional distance. And the way that we do this is using interleaving and H-gaps. This is what they call it in shell sort. The key to shell sort is knowing how to break the array down into subarrays. Subarrays are formed by taking an element, skipping H elements, and then taking the next element until the end of the array is reached. So you would count by 2s, or you would count by 4s. You would take every 6th element and sort it. The sequences of H values used varies by implementation, with different sequences being proposed by different researchers at different times. It's kind of interesting. Although, like, the overall algorithm is, like, well established, and it's a very, like, it's a venerable and well-used algorithm, there is still research going on with respect to this algorithm, and that's trying to find the optimal H-gap sequence, right? So we're sorting by different we're sorting by different gap sizes, but we don't know what the optimal set of gap sizes are, and that's an active area of research. So, different researchers propose different ones, most recently in 2001, so they haven't really moved on this in 20 years, so they're probably like, you know what, we're starting to hit the point of diminishing returns on this. But the most recent one is 1, 4, 10, 23, 57, 132, 301, 701, which I believe was this order was experimentally derived. No equation has yet been discovered which can predict the next number in the sequence. So this was like kind of done with brute force testing to see what the best runtime was. The worst case performance of this sequence is currently unknown. If you go to the Wikipedia page for shell sort, you'll see each one of these things, depending on the sequence of H-gaps you use, you actually get different runtime complexities, like different worst-case runtime complexities, which is kind of interesting. So here's a visualization of it, right? So let's say that you have an array, right, 0 through 11, let's say, and we're trying to sort it with h-gaps, with an h-gap of 5, right? So it's take 1, skip 5, take 1, skip 5, right? Another way of thinking about this is chopping the array in half, or chopping the array into chunks after you've hit the 5. So that would be h plus 1 elements. You count h plus 1 elements, divide the array, and then put it underneath, and then read them vertically. That's another way to construct these arrays, is sort of take a one-dimensional array and make it into a two-dimensional array. So with an h-gap of 5, you result in 6 subarrays. 06, 17, 28, 39, 410, and 511, which you can see are the verticals here. If we had the h-gap as 3, on the other hand, you can see we take 4 elements, chop, take 4 elements, chop, arrange them vertically, so you two-dimensionalize in that manner, and then our subarrays are 0, 4, 8, 1, 5, 9, 2, 6, 10, and 3, 7, 11. So there you go. That's how you create these subarrays. So, what's the time? We're not going to be able to make it. Well, we'll finish this next time, and in the meantime, I'll put up the Wikipedia page visualization of shell sort just for fun. But yeah, see, this experimentally derived one, it has an unknown worst-case runtime complexity. But you can see that, like, at the beginning, when they were trying to use formulas to predict them, you would get, like, big O n squared, or big O to the power of n, 3 over 2n, which is pretty good. N log squared n is pretty good. So we don't know what it is here, but the best ones that we have that were sort of before we started getting into these later ones, we were hitting n to the 4 over 3. The h-gap should depend on the array size, right? Well, no, not necessarily. It doesn't have to divide evenly, right? If it doesn't divide evenly, then you just have, like, 3 or 4 of your h-gap, 3 or 4 of your subarrays are like 2 elements instead of 3, something like that. The idea, though, is to keep the subarrays reasonably small to begin with, right? Because it's fast to sort a small array, and that's kind of like the question here, is like, is it faster to sort 4 arrays of size 3 than it is to sort 1 array of size 12? And you can kind of, if you didn't have to do any more swaps than that, assuming that after this step everything worked out, assuming worst case scenario, n squared, this is size is 12, so 12 squared is 144. Each one of these is size 3, so that's 9. 9 times 4 is 36. So you can see where the savings are coming from, right? But yeah. Do you need search and shell sort for the assignments? So yes, you will need to implement all 3 of these over the course of the assignments. Shell sort we save for assignment 3 because it's much easier to do once you know what pointers are. But yeah. So H-gaps are vertical or horizontal? Horizontal, right? It's like the H-gap is 3, so like 1, 2, 3. But if you were to take that and like if so the idea is you start with the red ones, you do that, right? Then you increase by 1 and then you count 3 again. That's why these are color coded, right? So it's like 1, 2, 3, next element, 1, 2, 3, next element, right? Then you return to the beginning of the array, go to 2, 1, 2, 3, 1, 2, 3, then you go back and you go forward again. What's the method of making these groups? It's just counting, right? When you make an H-gap, you're just counting. I was just wondering, I think assignment 2 has a question called binary search, and we have not covered it yet, so would the due date be pushed? What is the due date currently? Because we might have to push it, yes. Because it's unreasonable for me to expect you to implement something you haven't heard of yet. I was also thinking about pushing the midterm too, so that we can put pointers on it, because it really does make more sense to have midterm with pointers. Yeah, I suppose if we push, like, we've got 1 week of slack in the schedule that we could use, right? If we make, let's see, first day of exams is the 9th. So if we push the 28th to the 5th, yeah, it's gonna shift the whole schedule. But yeah, I think we're gonna have to. Yeah, I'll publish something today about it on the announcement feed. But yeah, we're gonna have to. You know what it was? I inserted that stuff on Git at the beginning of the course, and that messed up my whole jam. But yeah, I think we're gonna have to push everything back by at least a week. The midterm possibly by 2. I'll publish something about it. I'll make that decision today. I'll get it out to you guys. Git was really fun and interesting, though, so worth. Yeah, I find that Linuxy stuff to be very, very useful and valuable. If I were in a semester where I had more time, I would have worked things in a little bit more. Like at the moment, I've got a couple of topics, like a couple of more Linuxy type topics that I'm covering in the last couple of weeks of class. I would probably like work them in earlier because they're really useful and valuable, you know? Like, I don't think that you can really do a C course without doing make files, because make files are really, really useful and important. But, you know, it's like all of the assignments were set up, like, under a different scheme, and I haven't had time to, like, reconfigure the assignments. So, you know, yeah, I know it's kind of like, it's terrible for me to the prof to say, oh, well, you know, this offering isn't the way that I would have ideally wanted it to be. I might do it differently in the future. I know it's like, well, what good does that do me now? says the student. But, you know, I don't know. I don't think it's a bad thing that I'm wanting to improve the courses over time. I do think that the inclusion of the Linux material is an improvement. Like last year, there was like a very rough introduction to C++ in the last couple of weeks. And the problem, like you might say, oh, well, that sounds very interesting and useful as well. But the problem with C++ is it's such a huge thing to cover. Like it's impossible really to do it any kind of justice in the last 2 weeks of a course. So like the Linux stuff that I've inserted this time is more snack sized, so you can derive something useful and practical from it in just a couple of weeks. Whereas C++, it's like basically I'm just trying to tell you what like object-oriented programming is kind of like. But you know, technically speaking, everything we've done so far in class is valid C++ code because C++ is a superset of C. But yeah, anyway. Are there any more questions? No? Well, I guess I'll let you go then. Have a good break, everybody. Don't go crazy. Don't flip any cars, okay? People get mad when you flip cars. So, take her easy, folks.